Hello, this is Akanksha from ITE, and I'm here to give my tech talk on Outlook on Operating System. Outlook on Operating System. An operating system, OS, is system software that manages computer hardware and software resources and provides common services for computer programs. Time-sharing operating systems schedule tasks for efficient use of the system and may also include accounting software for cost allocation of processor time, mass storage, printing, and other resources. For hardware functions such as input and output and memory allocation, the operating system acts as an intermediary between programs and the computer hardware. Although the application code is usually executed directly by the hardware and frequently makes system calls to an OS function or is interrupted by it, operating systems are found on many devices that contain a computer, from cellular phones and video game consoles to web servers and supercomputers. Hardware complexity. Hardware is becoming increasingly more complex. Today, the programming manual for a system on chip SOS part of for a phone or server blade typically runs to more than 6,000 pages, usually not including documentation for the main application cores. Large numbers of peripheral devices are integrated onto a die, each with complex, varying programming models. More and more of these devices, networking adapters, radios, graphics processors, power controllers, and so on, are now built as specialized processors that execute specialized firmware with little OS integration. The OS communicates with these peripherals via proprietary messaging protocol specific to producers of peripheral devices. This marks the beginning of the trend toward dark silicon, a large collection of highly specialized processors, only a few of which can be used at a time. Energy. These systems aren't static either. As a system resource to be managed by the OS, energy is not just as important as CPU cycles, bytes of RAM, or network bandwidth, whether in the form of cell phone battery life or data center power consumption. Not least among the many implications for new OS design is the most of the hardware, such as cores, devices, and memory, can be powered up and down at any point during execution. Non-volatile main memory. As technology advances, we accept large non-volatile main memories to become prevalent. This doesn't only mean that most data will persist in non-volatile memory (NVM) as opposed to RAM or disk, but also that packing, cost, and power efficiency will make it possible to architect and deploy far more non-volatile RAM (NVRAM) than DRAM. Main memory will be mostly persistent and will have much greater capacity than today's disks and disk arrays. With large numbers of heterogeneous processors, this memory will be highly distributed, but perhaps not in the way we see today. Photonic photonic interconnects and high radix switches can expand the load stored domain where cores can issue cache line reads and writes across multiple server units within a rack or even a data center, and potentially flatten the switch hierarchy, resulting in more uniform memory access. Systems. Taking a step back, we see that the boundaries of today's machines are different from traditional scale up and scale out systems. The resources of a closely coupled cluster, such as a rack scale InfiniBand, than those used for traditional middleware. We're also accustomed to thinking of Linux or Windows as OSs because they started that way, that it's rare to consider a functional definition of an OS. Consider the following traditional definition of an OS. An OS is a collection of system software that manages the complete hardware platform and securely multiplexes resources between tasks. Linux, Windows, and Mac OS all fail this definition. A cell phone OS is a mishmash of proprietary device firmware embedded real-time executives, and the Linux or iOS kernel and its daemons that run applications and manage a fraction of the hardware. The OS of a data center or rack scale appliance is typically a collection of different Linux installations as well as custom and off-the-shelf middleware. If we want to examine the structure of a real-world contemporary OS, we need to look elsewhere. A great deal of traditional OS functionality is now occurring outside general-purpose OSs. It's moved to the top of rack management server, closer to memory side controllers, to various appliances, intrusion detection systems, and storage, or to specialized cores on the same die. Diversity. Hardware is also becoming more diverse beyond the complexity of any single product line of machines. The designs of every processor, SoC, and complete system are different. SoCs were always heterogeneous, but they they're used in are they're used in special purpose systems. Now they are used in general purpose systems. Engineering a general purpose OS that can be used widely and evolve as hardware changes, and with it, the trade-offs required for scalability, performance, and energy efficiency is a formidable challenge. Application changes. The ways in which computers are used and the applications that run on them are also changing, calling into question many OS designs of the last 40 years. This is both a challenge and an opportunity. It's a challenge because current OSs don't match up well with the applications they're called on to support. It's an opportunity because the burden of history, backward compatibility, long standardized APIs, and established programming models, for example, is light. Applications are very different now, granting us the freedom to change the OS interface. What's broken? It's remarkable how many assumptions about OS design embodied in modern systems like Linux and Windows are either violated or irrelevant. In light of the modern trends in hardware and application models previously mentioned, we are being deliberately provocative in this article, but we are also serious. We are certainly not the first to point out the deficiencies of current OS designs. Also note that the following issues are not bugs. They arise from the fundamental structures on which an OS like Unix or Windows is based. If you fixed them, you'd have a different OS. This naturally begs the question, however it ends up being branded, what will such an OS look like? Authorized and security. Unsurprisingly, an authorization and security model designed for a small work group of trusted interactive users, such as POSIX, or human members of a large organization such as Kerberos or Windows Active Directory, is inappropriate for online cloud services, application stores, virtual infrastructure platforms, single user handheld devices, and distributed applications. The security challenges we face today concern privacy, information flow, untrusted applications running with user privileges, and social networks with billions of users. At the OS level, at the OS layer, it might not make much sense to talk about traditional users. Human users installing and running programs they don't understand from third parties are the wrong security principles. Scheduling. Modern OS schedulers manage processes or threads as a basic unit of CPU allocation. But for modern multi-core hardware and typical applications, this is irrelevant. The recent increase in containers and virtual machines before them is a response to the fact that, astonishingly, no mainstream OS in the mid 1990s had an abstraction corresponding either to a complete application installation or to a running application instance. On a single machine, an application spans multiple processes and threads, and calls out to server processes it shares with other programs. Moreover, dynamic migration of threads to balance the load across cores, as in Linux, for example, makes no sense when cores are radically heterogeneous and where the objective is to optimize energy usage subject to fixed performance goals rather than the raw interactive response time or bulk throughput. Effective spatial scheduling rather than temporal scheduling becomes the key challenge. Virtual memory. Virtual memory is another strong candidate for change. Page-based address translation hardware was originally designed to allow appliances to use more memory than was physically present in the machine via demand paging. The OS abstraction corresponding to this hardware was a virtual address space magically backed with uniform physical RAM. Paging almost never happens today, and large machines in the future are likely to have much more memory than can be represented in the virtual address space. Data storage. Finally, POSIX-like files don't make sense at scale. Large-scale data processing applications access datasets through distributed parallel file systems like the Hadoop Distributed File System (HDFS) that expose how data is shared across storage nodes or through higher level record oriented distributed object stores. Files also disappear at the small end of the scale. Phone applications store their data in isolated containers through an API that hides any underlying Linux or iOS file systems, and in practice can transparently replicate such data across crowd services that use the data. The file as a concrete vector of bytes on local storage means little to most application programmers, let alone users. Its deserialized structure is what's important. Outlook. We conclude with a few bold, perhaps reckless predictions and some reflections on the process by which OS designs are created and evolve over time. Figure 1 usually summarizes our predictions. For more information, see the opportunities for a new OS sidebar. Architecture. The, the future OS will be distributed in architecture. A single kernel isn't going to work with heterogeneous processors, memory that isn't accessible from all cores, or partial cache coherence. There will be multiple kernels in a single machine, and some kind of message passing is inevitable. The result will be something between a single machine and a traditional cluster. The low message latencies of future hardware and performance requirements of parallel applications will necessitate much more global coordination and scheduling, memory allocation, and bandwidth allocation than is achievable in current clusters. I thank my lecturers for giving me the opportunity on speaking about outlook of operating systems.